In this video, we're going to continue with confidence intervals, and this time focusing a little bit more on interpretation, including some incorrect ways to interpret intervals and why they're so kind of tricky to notice why they're incorrect, and just some further details about confidence intervals as well. So here we go. So whenever we're looking at a confidence interval, like I said, there's several ways that we can interpret them wrong, and they're really kind of tempting to do. So we're going to look at an example here, and we have a couple interpretation options. And so what I'd like you to do here is kind of look at these different options for a second and think, which ones do you think are correctly representing what we've talked about before versus which ones do you think are not the way that we're supposed to interpret a confidence interval for a parameter. So take a moment and take a look, or I should say pause the video if you want to do that. I will go ahead. So in a study to try to find the average commute time for drivers in Chicago, researchers took a representative sample of 82 people who worked in the city limits. They used this information to construct a 95% confidence interval for the mean commute time of all Chicago workers. Their 95% confidence interval was 33.12 to 40.60 minutes. Okay, so option one, here's an interpretation. If I pick a random Chicago worker in the city limits, we are 95% confident that their commute time is between these times. Okay, so notice that this statement is describing confidence in an individual's commute time. So we have this wording here, that their commute time, so pick a random Chicago worker, that their commute time is in this range. The answer here is no. So this is not an appropriate interpretation. Oops, don't know what I was thinking there. Okay. And that's because a confidence interval is not telling us where 95% of the individuals in the population are. That would be the standard deviation, or like the 1.96 standard deviation ranges for the observations could help us with that, but not a confidence interval. And so if I go back to this picture that we've seen before, remember that a confidence interval is talking about kind of this scale right here, that we have an x bar that's somewhere in this range, and we're going to stretch out kind of this certain distance to try to capture mu based on where we are in this distribution. Our confidence interval, though, is not necessarily going to capture, in fact, it isn't going to capture where 95% of individuals in this population are, because there's a lot more range here, as you can kind of see, right? So, so 95% of individuals might be like from here to here. So that is not what our confidence interval is going to be doing in trying to capture the true mean. So what you're probably thinking of here is if I stretched out 1.96 standard deviations when looking at individual observations, but not 1.96 standard errors of our sample mean. We are 95% confident that the average commute time for all Chicago residents is between these two times. So this is a yes. This is kind of our textbook interpretation that we're going to go to. We're 95% confident that the true parameter, the average commute time of all Chicago workers, is between these two values. This one's very tempting as well. 95% of the 82 workers sampled take between these amount of times for their commute. So again, not true. It's kind of not true for the same reason that the first one's not true, is that an interval is not telling us about the location of individuals. We don't know where 95% of individuals are. We know we're 95% confident where a parameter is located. So this is a no. The next one, we are 95% confident that the average commute time for my 82 workers is between these two values. Okay, so let's think about what this statement is. That the average commute time for my 82 workers, that would be x bar. That would not be mu. So right up here, for example, the average commute time for all Chicago residents. Oh, you know what? Sorry. Let me, I always forget to fix this every time I teach this class another semester. Let's pretend that said workers. So So you might be wondering, wait a second, that's not the same population, and you would be correct, I guess. So we're not making a confidence interval for Chicago residents. We're making a confidence interval for Chicago workers. So let's just pretend that's what it says, so that it works. Okay. So down here we get to number 4, the average commute time for my 82 workers. This is x bar, not mu. We know what x bar is already, right? Because we have our sample information. X bar is the center of our interval. So it wouldn't really make sense to say that I'm 95% confident where x bar is, because I'm actually 100% confident where x bar is exactly. So, so this is a no. We are already 100% confident where x bar is. And I'll kind of add to these as well. So CIs are not claims about the position of individuals. Isn't that right, Truffles? It's not. And then the last one's kind of the same thing. So ditto, not a statement about individuals. Okay. Last one. So this is an interesting one. I'm curious what y'all would think. I mean, I guess I can't really talk to you live, but I am curious what y'all think. If I completed this study 100 times with 100 different random samples of 82 workers, I would expect approximately 95 of my 95% intervals to contain the true Chicago average commute time. This technically is correct. It does work. It's just kind of a convoluted way of saying it. And so I mention this because if you take higher level stat classes, this language, as convoluted as it is actually kind of the preferred language for interpreting a confidence interval, because this first one up here is nice and simple, but it's a little bit, there's some reasons why some folks maybe don't like that language as much, but this is kind of a preferred language in higher level statistics and inference and thinking about confidence intervals. So if you think about what's going on here, is it's saying that if I continuously sample and produce confidence intervals from each of my samples, and they're all samples of the same size, then I would expect that about 95% of my 95% intervals will contain the parameter, and 5% of my 5% intervals will not. So if you think about it, that is literally what a confidence interval means, is 95% of the time the interval works, 5% of the time it doesn't. So that's kind of what I'm expecting to happen if I do this 100 times or 500 times or whatever. So just keep that in mind, that this is another way to think about it, that maybe it's a little bit confusing, but maybe it's also just kind of a helpful reminder of what it is. It's a probabilistic statement about where the parameter exists. Okay, so this is good. Boop. Yes. So just some reminders. We already said this. It's a statement about the position of a parameter, not a statement about the position of individuals. It shouldn't be used to make claims about our sample as well. So we're not making a statement about where x bar is. We're making a statement about where mu is, this thing that we don't know. We've already talked about this part, so I'll kind of skip through it, but just choosing a confidence level that the more confident you want to be, the more standard errors you need to stretch out, the more the margin of error increases. So confidence is great, but there's a cost, right? So more confidence means more range, more uncertainty, sort of, and where that parameter is going to be. Same is true for the opposite issue. So I can pick a smaller confidence level, but and I can get a more narrow range, but the less confidence I have, then obviously the more I might miss it. So I want to tread cautiously going the other way as well, which is why 95% for whatever reason is just a very commonly accepted appropriate level of confidence. Sometimes I know some folks who prefer like 99% confidence intervals or 98%, so that's very common to see as well. But 95% is a very standard route to go on these kinds of things. If you read like a poll, for example, what they'll typically do is they'll report their point estimate. So like, a presidential approval rating or something like that, they'll report their point estimate, say 50%. And then they'll also provide like a margin of error. So for 95% confidence, the margin of error is between this value and this value. Again, they could do more, but that's just kind of a standard that you see. We also talked about this already, but decreasing the margin of error. So there's two ways to do that. One is to just go with less confidence. The other is to increase your sample size for the same reason we mentioned before, that if you increase your sample size, you have a kind of a narrower sampling distribution, right? Because you should have more accurate sample statistics possible. So then your standard error is going to go down. So that margin of error calculation is going to get smaller and smaller when you do that. So that's another way to kind of decrease that margin of error besides decreasing confidence. There's also some assumptions that we've kind of alluded to already. One that I definitely mentioned here is that we need to ensure that the sample is collected in such a way that it is representative of the population we wish to generalize to. So any external validity threats should be noted as limitations when we're doing this. So if you look at polling, for example, they can't get random samples of people because people say no and because some people are hard to reach. So there's things that they do some weighting of their sample to try to either work harder to get certain hard to reach groups, or they weight the responses of some people more than others to make up for the fact that they know that maybe, I'm trying to think of an example, people who work a lot of jobs, maybe have a lot of kids, people who are maybe young people who aren't home or just don't answer the phone much, maybe they know that they're harder to reach. And so as a result, those samples or those kind of results get weighted a little bit more in the poll results. So basically, whenever we're doing this, we're assuming that we have done this correctly, that we either have a random sample or there has been something done to ensure appropriate representation of the population such that we are simulating getting a random sample from this population. If this is not true, then this is a limitation and it's something that should accompany the results that you share. Second goes back to the previous chapter, and that is that we're assuming, so we're doing what's called a parametric method, a confidence interval using parametric methods. That means that we're assuming the distribution of possible sample means follows a normal distribution. We're using normal distribution properties to approximate where our sample mean is located and what that distribution of sample means looks like. So that's an assumption that won't always be true. So if you go back to this example, for example, this population itself isn't normal, but we also know because of the central limit theorem that sample means tend to distribute normally around the parameter given that the sample sizes we're taking are large enough. But there's going to be some cases where the sample we're taking isn't large enough. So if I have a population that looks like, maybe it's just like really skewed, maybe it's like this, just something like really crazy. 30 may not be enough in this context. So we need to be really careful about this and think about the variable that we're working with and how skewed it might reasonably be, because the more skewed it is, the larger the sample we need to make this assumption that this is going to be a normally distributed distribution of possible sample means. So I bring that up here because it's an assumption that we make, and there's going to be some times where we can't make this assumption, and we should either not do a confidence interval or we should do so very, very cautiously. So if our population is already normal, or it's already kind of close to normally distributed, then we're probably fine. Then for pretty much any sample size we're working with, we're probably okay. When our population is not necessarily that shape, then we need to have a sufficiently large sample. Now in our class, we're going to go ahead and just kind of say that if our sample size is greater than 30, or at least 30, honestly, I'll just make that just to clarify this right now, 30 or more, we're probably okay in most contexts, unless we know something about the population, unless we tend to think it's really skewed. But in our class, we're just going to say that we need one of these things to be true. Either normal distributed population or close to it, or a sufficiently large sample size, in which case 30, we'll just wave our hands and say is probably good enough most of the Also, one other note that we don't really care too much about in this class, but just a note. Whenever our sample comprises a hefty proportion of the population itself, like if we have more than, say, 10%, at least more than 5%, and certainly more than 10%, our standard error is going to slightly overestimate the true standard error, because these methods are assuming that we're sampling from an infinite population. The way that the standard error calculation works is it assumes that there's this infinite population and we're kind of approximating how much variability we should have in our sample mean. So whenever this is not true, whenever we do actually have a notable proportion of the population in our sample, we just want to keep in mind that our confidence interval is probably overestimating how wide we need to be. We're really not going to worry about that in this class. It's more just something that I mentioned because some people wonder about this or have brought it up to me before. So it is a thing, and there's ways to correct for this that we won't worry about in this class. So otherwise, we can trust our intervals, and whenever we have a large proportion of the population in our sample, we're just going to note that our interval might be wider than it actually has to be. Okay, so a researcher would like to create a 95% confidence interval for the average amount of time that UIUC students spend streaming movies and television shows a week. I don't even know if we still call them television shows. This is a good question for me. I still grew up in the era of television where you literally watch the television, but now I feel like we live in a time where this term doesn't make any sense. A series, I know somebody who just calls everything movies. It doesn't matter if they're like a movie or like a series of shows movie. Okay, I'm going to stop talking about that. She has a random sample of 24 students who filled out this information. She also has reason to believe that the distribution of times is somewhat symmetrical and close to normally distributed. So in other words, that this population distribution itself should be pretty close to normally distributed for whatever reason. So given this information, are the assumptions met to create a confidence interval for the population mean? So what do you think? So based on what we talked about here, are we meeting these conditions? So the first condition is that our sample is representative of the population we wish to generalize to. So she has a random sample of 24 students. I don't exactly know how she did that, but if this is true, then technically, number one, representative sample, check. If it's random, then it should be representative. I know we could probably talk about this of well, is 24, if you have a random sample of 24, is that representative? And so the answer is yes. If it is truly random selection, then it is always representative because it is coming from that population appropriately. If it was a convenient sample, not necessarily. The second assumption that we have here is the distribution of possible sample means when n equals 24 going to be normally distributed? Can we use these normal distribution properties to make an inference about where our sample mean is in relation to mu, assuming this all falls in a normal distribution? And so the answer here is, so I'm going to say normally distributed sample means. And the answer is probably yes, because of this. If we believe that the variable itself is already pretty close to normal, then even if our sample size isn't that big, even if it's not past 30, then we can still probably assume that the sampling distribution is probably normal because the population itself is already pretty normal. So if our population looks kind of like this, maybe it's not perfectly normal, but maybe it's pretty close, then our distribution of possible sample means is probably going to look like this. That's not perfectly centered, but something like that. So as long as the population itself is pretty close, the distribution of possible sample means should be pretty close, or should be normal as well, even if n is not super large. Even if n is 24, that should work here. So we got one of those two conditions, and we just need one of the two to make that assumption.